So one of the other things that the ideal gas law can be used for is to determine molar masses. Now, of course, ideal gas law, right? So this can only be used if the sample can be turned into a vapor. So you wouldn't be able to determine the molar mass of like copper, for example, using this technique. Even water, for an example, you would have to boil the water first and measure everything in the gas phase. You would have to measure it as steam in order for this to work. So for liquid water directly, this wouldn't work. So to see an example of how this is, we have an organic chemist isolates a colorless liquid from a petroleum sample. She isolates the following data. So we have the volume of the flask. So if we're going through and identifying things, we have our V, it's 213 mLs. We have our temperature as 100.0 degrees Celsius, and we have our pressure as 754 torr. So right away, we kind of see that this feels like ideal gas law because we have 3 out of the 4 variables. And so, of course, we know that R, we can always look up R. And so liter ATM per mole Kelvin. And so from that, we can find N. And so we also then have 2 other pieces of data. We have the mass of the flask plus gas, and we have the mass of the flask presumably empty. And so from that, we can get a tare mass. And so what you have to assume in this problem is that we're taking this liquid and we're heating it. And so there has to be, a vaporized process that happens here where we vaporize the liquid into a gas. And notice that the temperature here is 100 degrees Celsius, so we're probably heating this up well above, its boiling point. So what we can do is figure out the mass of the sample by subtraction. It's just tare mass, so we can subtract the empty flask from the mass of the sample. And so when we do that, we have 77.834. And so if we subtract those, 78.416. If I don't punch buttons wrong again, there we go. And subtract that, so we get 0.582 grams is the mass of our sample. And remember that what we're trying to find here is molar mass. The units on molar mass are grams per mole, so what we need is the mass of the sample divided by the moles of the sample. And we just have figured out most of that. So we have our 0.582 grams as our mass, and our moles now we're going to get from the ideal gas law. So if we take PV equals nRT, and we divide both sides by R and T, we get PV over RT, and that gets the N by itself on the other side. And so now we can plug in, but we do have to double check our units. So the volume here is given as milliliters. In R, our unit is liters. So we're going to need to divide by 1,000 here and make this 0.213 liters. The temperature is in degrees Celsius. We're going to need to add 273.2. And so that'll give us 373.2 Kelvin. Again, remember it's 273.15, but we're only going to the tenths place, so we can round that 0.15 to just 0.2 in this case. And then our 754 torr, to go to ATMs, remember you want to divide by 760. So when we do that, it's very close to 1 ATM, but just slightly below, so 0.992 ATMs. And now all of our units, liters, Kelvin, and ATMs, match the 3 of the 4 units that are in the constant, so we can just plug in, and those units will work out for us. So 0.992 times our volume of 0.213 divided by our constant, 0.08206, and our temperature of 373.2. And so when we divide all of that out, we get 0.00690 moles. And now we know the grams of our sample, and we know the moles of our sample. So if we just divide them, that tells us the molar mass of the material. And when we divide that out, we get 84.3 grams per mole. Now, we don't necessarily know anything else about this sample here. If we had like mass percent data, for example, we could figure out the empirical formula of the compound. And now that we have the molecular form or the molar mass, we could figure out the molecular formula if we had that extra info. But again, in this problem, we are given only enough information to find the molar mass. So we really don't know anything else about the sample, whether this is an element or a compound, what elements are in it. We don't really know anything else. We just know the overall molar mass.